All right, so now we're going to get a closer look at that constant. Really, that was what we were just talking about just now. Okay, so think about that function right there. What's the vertical intercept? And we had actually already figured that out. There's two ways to figure it out. It's going to be the constant at the end, but if I don't realize that, well, then I plug in t equals 0, and I get a height of 1450. So my vertical intercept is 0, 1450. What's the practical meaning in this situation for this ball being dropped from the tower? This was the initial height of the ball. So predict what the graph would look like if the constant were changed to 800. Okay, so then it would end up being, the graph would still be, it still has a negative 16 in front. You're going to see what that does to it. But it would end up being not as high. Okay, so if you graph that, now our sketch before when I had 1450, looked something like this. If I did it now, it would be something like this. Okay, similar shape, but it would have a lower initial value. Okay, so in the constant term in the quadratic always indicates the y-intercept. So we just actually figured that out before anyway. Okay, so you can get it two ways. You can realize it's c at the end, or you can plug in 0 for all your x's or your t's in this case. So I want you to stop the video right now, okay, and I want you to do number 8 on your graphing calculator. And I've got my graphs already done here, so you are going to just do a little sketch. I did them all on one. Do a little sketch of each of those. I think there's how many? 4 or 5? 4 graphs. And look at what's changing in there. Each time our A is 1.5, but we're varying the y-intercept. So take a good couple minutes, sketch them, and then come back here and take a look at my graphs. Okay, so all of them are the same width parabola. Okay, they're all opening up, and you're going to see that that's because of the 1.5, that it's positive. And each one just has a different y-intercept. So I wrote next to each one that this one, the first one, doesn't shift at all up or down because there is no constant. B shifts up 7, and C shifts up 4, and D shifts down 4. So that all had to do with that C being moved around. All right, so then we're going to compare the one we had before, the negative 16x squared, and we're going to compare it to a positive 16x squared. So over here I have both graphed. The green one is the initial one, and then the blue one, I'm kind of tried to color code these for you. The blue one is the blue graph, and that's if I made it a positive 16. So that one, the only difference in there is it had the same y-intercept because 1450 was the same, but the second one, the blue one, opened up. So what effect does the sign of that one have on the graph? Okay, well the sign, it's changing, it determines if the graph opens up or down. So you see when it's a positive 16 it opened up, and a negative 16 opened down. Alright, so now we're going to not only vary the sign, but now actually, so we figured out what the sign of that A does, but now we're keeping the sign consistent. All these signs in each of these three they're giving us, they're all negative, so you notice every one of these graphs is opening down, but we're changing the size of it. Okay, so you're going to look, this one over here, I got color coded these again, the blue one, so I want you to sketch each of these on your calculator and see what happens. So in this, the blue one ends up being the widest of the three, and then the red one, and then the green. So you can see as that number, as we look at the magnitude of the number, not the sign, but the actual magnitude of that A, as it gets bigger and bigger and bigger, the graph gets more narrow. So as the magnitude of A gets larger, the graph gets more narrow. Okay, so and actually they wrote this right down here for us. Okay, the magnitude of A affects the width of it. The larger the absolute value of A, meaning the magnitude, the narrow. So if I were comparing a graph like this versus something like this, okay, this one right here is going to be wide, and this one's going to be more narrow because our A is getting larger than the 1/2. Okay, so actually they're asking us the same kind of question next. So is the graph of h of x equals 0.3x squared wider or narrow than this one? So this one right here has a 1. Okay, so this one is wider. The one with the 0.3x squared is wider. How does the output values of h and the output values of f compare at the same input? So in this one, the output of 0.3, that 0.3x squared, is smaller than the other one, than of x squared. That's what makes it wider. Okay, because this one has a smaller output. Let's just say that the x squared is like this. Well, then the other one has smaller outputs, which makes it wider because the y values aren't as large. So is the graph of 3x squared wider or more narrow than the graph of x squared? So a 3x squared is going to be more narrower, because their output values are larger for the 3x squared than the x squared. So describe the effect of magnitude on the coefficient A and the width. Okay, so that's what we wrote up right up there. The larger the magnitude, the more narrow the graph. And the larger the magnitude again, the larger the output values. Okay, so the next part we're just going to look at really quick is what happens if we vary. We looked at varying A, we looked at varying C. Let's look at what happens if we vary the middle term. Okay, so you're going to take two graphs, one that has a -40 in the middle linear term and one that has a +40. So take a minute and sketch them on your calculator and see how they change. See how changing that middle term does to things. Okay, and I've done a couple before here. So what I did was I graphed all three. The original one without a linear term, then the one that had a -40 linear term, and the one that had a +40 linear term. And you can see from our three graphs, our original one is the blue one. And then when I added a 40t and subtracted a 40t, this is what happens. It shifted my graph horizontally left and right. Okay, so no longer is the vertex, this turning point, what we're calling the vertex, is not on the axis anymore. This one, my turning point was on the axis. Okay, once I add that linear term, it shifts things right or left depending on the sign of it, and it means my turning point is not on the y-axis. So what effect does it have on there? Okay, it makes it so that the turning point, okay, later on, I'm not sure if they call this the vertex yet, but we will, is no longer on the y-axis once I add in that linear term. Okay, if b equals 0, like the initial one, okay, then the turning point is right on the vertical axis. If not, it starts moving left and right. Okay, so I'm actually, for number 14, again, I want you to try it on your own first. I want you to go on the graphing calculator. Although first, the best thing to do is do some predictions. Okay, before you actually graph them, kind of think about if they're going to open up or down, what the y-intercept is, if it's going to shift up or down. You can set your windows exactly what they have right here, so you can get a nice picture and a nice sketch. Okay, and then once you're done, take a look at mine. Okay, the A is just the initial kind of quadratic that has a y-intercept at 0. Then C shifts it up 4. E shifts it down 3. Okay, and then B and C is kind of, B and D, they're all opening up because A is positive in all of them. But B and D has a different turning point, not on the axis anymore because of that linear term. This light blue one, I know it looks like the vertex is right on the y-axis, but it's not actually because of that X in the middle. I just could not get it to look right when I drew it several times. For this one, 15 is to match each function with what its possible graph could be. So even before, I would rather you do them not even on the calculator. I'd rather just look at each one and kind of figure out which one, the easiest one to pick out first. If I look at C, that negative x squared plus 3x, it has to be the one opening down. Okay, so this one right here must be the graph of C. And then between the other two, it's a matter of, this one has a middle term. A has a middle term where B doesn't. Okay, so B is just going to be one that's a little bit wider because of this, 0.2, and shifted up 4. Okay, so that one's going to match with A. And if you notice, sorry, I wrote that wrong. I meant to write B. And if you look at A, and it has a middle linear term, which means the vertex is not going to be on the y-axis anymore. It's not the same as the y-intercept, so that must be this one, because this one is shifted a little bit left to the axis. So down here you have a nice summary of what we just talked about on what A does to my graph, what B does, and what C does. And so you can practice these activities, especially the ones where it's having you, for instance, numbers 6 through 10, are great exercises to kind of just get an idea of what each graph looks like. And then we'll just continue to add on to this as we go through this chapter.